Good morning. My name is Carlos Gaviria, and I recently graduated as a PhD in software engineering from University College London. Today, I will present the PhD paper I wrote with my supervisors. In his book, Paul Butcher describes his experience battling with priority inflation when working on a bug fixing team. Because the team had a heavy workload, developers only had time to fix high priority bugs. Testers realized that if they want their bugs fixed, they needed to report them as high priority, even if they were, in fact, low priority bugs. Over time, the bug tracking system became inundated with high priority bugs. When everything had a high priority, the bug fixing team was no longer able to prioritize their work. Priority inflation occurs due to incentive problems in the prioritization process. If testers want the bugs they report fixed, letting them prioritize bugs results in inflated priorities. Game theory is a well-known approach for addressing incentive problems. Game theoretic models can predict the behavior of rational agents in scenarios where they interact. Let me illustrate this with an example. In the slide, we're modeling two testers, Alice and Bob, where each tester has two actions: to be honest when reporting priorities or to inflate. A cell in the payoff matrix contains the payoff for each tester given their actions. In this game, a tester receives a bonus depending on bugs fixed and their priority. For example, in the top right cell, if Alice reports priorities honestly and Bob inflates, she receives $100 while Bob receives $150. Given a payoff matrix, a game solver can obtain player behavior at equilibrium. Behavior in a game theoretic model is defined in terms of strategies, which assign probabilities to each action. In our simple game, both Alice and Bob have the same strategy at equilibrium: inflate priorities with a probability of 100%. Any prioritization process this game models is susceptible to priority inflation. We use this methodology to analyze industrial prioritization processes to see if they are susceptible to priority inflation or not. The first process we analyze is distributed prioritization, where the person responsible for reporting bugs also assigns their priority. Then we move to the gatekeeper process, where a different team, typically a bug triage team, prioritizes bugs. To build our payoff matrices, we adopted empirical game theoretic analysis. We obtained payoff values via simulation, and the strategies and simulation inputs are inferred from data. We use an Apache Software Foundation dataset, built mining their Git and Jira repositories. This slide shows the results of our equilibrium analysis. A bar in this chart corresponds to the equilibrium of a prioritization process, where each strategy has a color assigned. The undesirable always inflate strategy has the color red, while our target honest strategy has the color light green. Distributed prioritization on the left has a probability of 100% for the always inflate strategy. The same happens with a gatekeeper that detects 50% of inflated priorities, and with a gatekeeper that detects 90% of them. For an ideal gatekeeper that detects every inflated priority, we obtain 3 equilibria. In none of them, we obtain the desired outcome of honest reporting with 100% probability. These results show that industrial practice is susceptible to priority inflation. To solve this problem, we propose assessor throttling, a novel prioritization process designed to address priority inflation. Like with distributed prioritization, reporters are in charge of the initial priority assessment. This assessment is later evaluated by the developer that fixed the bug. After coding the fix, developers are in a good position for priority assessment. If they disagree with the priority assigned by the reporter, they can penalize them by diminishing their reputation. The reputation ranking of reporters later influences what bugs developers work on. The higher the reputation, the more likely they'll get developers' attention. The assessor throttling process has one parameter: the penalty developers apply when they disagree with the priority assessment. As shown in the slide, a penalty of 3% is not enough for incentivizing honest reporting. At equilibrium, we obtain always inflate and empirical inflator strategies. However, with a 10% penalty, we obtain immunity to priority inflation with 100% probability for honest reporting. Assessor throttling relies on developers fixing more bugs from high reputation bug reporters. The FED is the software tool that enables this. It is a Chrome plugin that connects to Jira's API to produce a list of open bugs sorted by reporter reputation. It is an open source project available on GitHub that we hope enables the adoption of Assessor throttling. To conclude, we have showed how to diagnose and fix software process problems using game theory. We believe priority inflation is only one instance of many incentive problems affecting software development. I invite you to read our paper and apply game theory to solve the problems affecting your organization. Thank you very much.